In this video, we will prove that if f of x equals to x power, then the derivative f prime of x has to equal to n times x to the n minus 1 power. That's our goal. First of all, let's show the first few cases first. Remember that the definition of the derivative, f prime of x, we can write it in this form. It's the limit as x goes to 0 of f of x plus h minus f of x over h. That's our definition. Now let's try some cases. If f of x is equal to x squared, then that means that f prime of x has to be the limit of as x goes to 0, x plus h squared minus x squared over h. That equals the limit as x goes to 0. X plus h squared is x squared plus 2xh plus h squared minus x squared over h. The x squared terms cancel, and we end up with the limit as x goes to 0, 2xh plus h squared over h. The h terms cancel. And we have the limit as x goes to 0 of 2x plus h. Well, if h goes to 0, that means that this term goes to 0, and we end up with 2x. So that's why the derivative of x squared has to equal 2x. Well, let's change the x squared to the third power and see what changes in our proof. So this time I'm changing the 2 to a 3. That means that x plus h squared becomes to the third power. X squared minus x squared becomes minus x to the third power. Okay. Well, that means that this becomes the third power. And this time we're expanding x plus h to the third power instead of x plus h to the second power. If we expand it, we get x to the third power plus 3x squared h plus 3xh squared plus h to the third power. So third power. Once again, the x to the third power term cancels. Here's what we should notice. The whole term here, the entire term here, 3x squared h plus 3xh squared plus h cubed. We divide by h. Really, whatever we get, the only term that matters is this one, the 3x squared h term. That's the first term that's the only term that matters. Why? Because when we divide by h, let's write it out. When we divide by h, we have 3x squared h plus plus 3xh squared plus x cubed. When we divide by h, that's the only term that doesn't have an h in it. So that's limit as h goes to 0 of 3x squared plus 3xh plus h squared. Of course, all the other terms have h in it, so they go to 0. So when we expand this, x plus h to the third power, the first term we know must cancel out the last term. The only term that matters is the second term in our expansion. Okay? Alright. Now this time, let's prove the general form. We will still have to go back and think a little bit about algebra, about precalculus. But this time we do x to the n power. X to the n power. That means that we're going to have limit as x goes to 0 of x plus h to the n power minus x to the n power over h. So the hard part really is, again, this is called the binomial expansion, x to the h to the n power. What's that going to equal? Well, let's take a step back. X plus h to the second power is x squared plus 2xh plus h squared. X plus h to the third power is x cubed plus 3x squared h plus 3xh squared plus x cubed. X plus h to the fourth power is x to the fourth plus 4x cubed h plus 6x squared h squared plus 4xh cubed plus h to the fourth power. You can calculate it by just manually multiplying these out, like x plus h times x plus h times x plus h times x plus h. But really, an easy way of thinking about this is we see that if this is squared, we have squares at the end, and then this power is going to be 1 and 1. If it's cubed, we have cubed at the end. Second term is x squared, x to the 1 power. Third term, x to the 1, x to the second power. Last term is x cubed. When it's x has h to the fourth power, is x to the fourth plus 4x cubed to the 1 to the 1 power plus 6x squared x squared plus 4x to the 1 power x cubed plus h to the fourth. So we see the pattern in the exponents. And then finally, the pattern in these coefficients. We can figure this out from Pascal's triangle. It looks like this. 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, and so forth, where each number is the sum of the two numbers on top. Okay. But really, remember from our proof, the only term that really matters is the second term. The first terms will cancel this part out, the x to the n term, and the rest of the terms go away. They will go to 0 as h goes to 0. So none of the other terms matter. Look at what happens. In x plus h squared, the coefficient of the second term is 2. In x plus h to the third power, the coefficient of the third term, second term is 3. In x plus h to the fourth, the coefficient of the second term is 4. Okay. Now we're ready to go back to the general case. So let's go back to the general case. F of x is x to the n power. F prime of x is the limit as h goes to 0 of x plus h to the n power minus x to the n power over h. Expand out. And we know this is x to the n power plus, remember the coefficient in the second term is always just n, times x to the n minus 1 power times h, and a bunch of other terms that we don't care about because we know it'll cancel out to 0, minus x to the n over h. Again, the x to the n term cancels out, and we end up with limit as h to the 0 of n times x to the n minus 1 times h over h, plus a bunch of terms that go to 0, divide by h on top and bottom, and we get the limit as h goes to 0 of n times x to the n minus 1 plus a bunch of terms that go to 0, and that's just equal to n times x to the n minus 1. So we've proven this. If f of x equals x to the n power, the derivative f prime of x must be n times x to the n minus 1 power. That's it.